Yeah. Okay. Okay, so in the previous part, we introduced two-layer neural networks, and we said that they're sort of prototypical object of study for mean field theory. This is indeed where the first convergence results to the distributional dynamics that we presented last time occurred. In fact, the paper that we're reviewing today is actually one of the first papers to get a similar result. So this is why I think it's kind of topical, and it's an important milestone for the field. I'd like to spend some time describing sort of the main results there, and also kind of hinting at some of the ideas involved in replicating these results in more generality in other settings. Okay, so again, a quick recap from the previous part. We have a two-layer neural network, which is a sum over neurons and activation functions. Typically, we'll just subsume all of the weights into a single activation function that depends on the data and the weight vector theta I. And the idea being that we have this sum over individual neurons, each given with the individual weight theta I. You see this sort of prototypical mean field scaling taking place here, and this is going to become important for basically reinterpreting f hat as a kind of a law of large numbers for the weight distribution. Okay. The risk is given by an expected squared loss over the data distribution given by y index. And again, what we remarked last time was that these functional forms benefit from a particular type of symmetry, right? Which is to say that even though the risk is written in terms of theta, here actually it only really depends on the empirical distribution of the theta weights. The empirical distribution obviously being an average of delta functions over individual thetas. Okay, and viewing it this way, you can also decompose it as a constant plus a sum of first and second order terms. And this expression is going to become important for describing the sort of proposed asymptotic limit of the risk as we move along. So okay. So why is this typically important? Is because of sort of probability measures such as this. They fit into a particular framework that is already well studied in mathematics, belonging to either chaos theory or ergodic theory. This is particularly relevant because it allows us to write down phenomena that depend on not just the individual trajectories of the weights and random variables, but also on the relative interaction with the distribution of other particles of such kind, but irrespective of individual pairwise interactions. So this particular setting is called chaos or Kak-type chaos, and a sequence of probability measures on a product space is called chaotic if the sequence is symmetric, so you can define the kth marginal uniquely, and the kth marginal of the nth element in the sequence tends to a k product of some probability measure on P weakly. The important thing to remember about this is that you can also replace this condition by just the condition that we saw in the previous slide. Namely, you can replace it as a convergence of the empirical measure to the probability measure Q, where the empirical measure is taken over samples x1, xn from Qn. So you can actually view this as a definition. You can view this as a definition of the type of probability measures that we have under scope. And in particular, whenever you see this type of behavior, well, then it means that maybe there is some sort of mean field behavior lurking behind the scenes. Okay. Okay, so we would like to somehow formalize the idea that as we keep taking gradient steps on the weights, somehow by adjusting the rate of stepping and the width of the layer of the neural network, then we will approach this sort of distributional limit rho t that we presented last time, and I'll rewrite it in a second. But it is sort of in some sense in which all of the appropriate quantities that we observed before, such as the outputs f and the risks, they tend to their sort of appropriate integral versions, right? So this is replacing the sums by integrals over this limiting distribution, right? So just viewing the previous finite sums as integrals over the empirical distribution. Okay, and again, you want rho to be a weak solution for the distributional dynamics equation. This is something that we presented in the previous lecture. And we said that we're going to look at two particular flavors of this. Okay, we're going to look at kind of standard gradient descent and at noisy gradient descent. Remember, noisy gradient descent was defined by, at each particular step, adding a kind of some independent Gaussian noise with amplitude or with variance beta. So the corresponding dynamical equations that we would like to see occurring for rho t are in this case of standard SGD given by this, where the potential phi is constructed from V and U, which are the first and second order elements of the risk. And again, for noisy SGD, you have this this extra heat diffusion term, where you see the sort of the beta parameter coming in, so the temperature of the magnitude of the Gaussian noise that you're adding in the SGD steps coming through. And you also need a certain regularization parameter here. This is mostly for the proofs making sense in this setting.
I just wanted to give a brief comment, perhaps to make some connection to people if helpful. I think the question on top, well, the question on bottom, so 63 is basically a Fokker-Planck equation associated to a given stochastic differential equation that would be the noisy SGD, I guess. I mean, equation 63 is not the equation, is not the SGD itself, right? It describes the evolution of the probability density under some stochastic differential equation that is equivalent to SGD, right?
Yes.
And And while the question on top, 61, well, it's the same as it's the same but without noise, and it's basically a continuity equation. So there is a flux. So it's like an equation that describes the flux of probability. Well, I guess also 63 can be considered a continuity equation. Anyway, I just wanted to I wanted to ask a question. I didn't understand precisely why. So psi is this, what physicists will call the potential, I guess. So why?
Well, I
sorry.
I called it a potential. I don't know if they call it a potential in the paper.
Yeah. So psi is why is it? Are we using a approximation to second order of psi? I missed that.
It's not an approximation to second order. This is an equality. So okay. This is exactly what it equals, and that's a good question. And this is because let me go back. This is again not an approximation of the risk. This is an exact computation of the risk, and also for the finite risk. So if you go back to the finite version of the risk, this is an exact computation. It's a quadratic in the parameters because the neural network is a two-layer neural network.
Okay, so it's because it's two-layer, then we can so that's why the potential is quadratic.
Yeah.
So if you have more layers, then it's not.
If you have more layers, it's more complicated. So it's still independently quadratic, I think, in each of the, well, okay, with again these v's and u's, these are not linear functions. So it's quadratic in these v of theta I and in this v of theta I potential and u of theta I theta j kernel. But the point is that you can find an expansion in terms of this for all individual parameters, right? Even in a deeper network, but you might get some products coming in if you have deeper networks.
Okay.
So you'd expect some even higher order terms here.
Yeah. Okay.
Yeah. Okay. Yeah. Thank you for that question. I think that's quite relevant. Yeah. So this is kind of an exact example of what this is. Maybe we can I can quickly go back to the slides from the previous time, and we can actually show what the expression for this is. So R0 is just the expected value of the dependent variable. V is the expectation of this activation function with respect to the data, and U is this expectation again of the product of the activation functions with respect to the data. So if you substitute these values in, then you just get back the risk from the original formula. And the idea being that now you would like to assume that these expectations are not taken over an empirical distribution and just write them as an honest integral over some distribution of the weights. Okay. So I think we were here. Yeah. Right. So exactly. So as Alberto observed, and also why we spent time looking at the Fokker-Planck equation the previous time, is this indeed does look like a Fokker-Planck equation. It is very subtly different from a Fokker-Planck equation in that the potential psi depends on the weight distribution itself. So in a typical Fokker-Planck equation, you wouldn't have this dependence here. Okay. Moving on. Okay, so for these types of equations, there's kind of classical theory that shows that solutions exist and are effectively unique under sort of reasonable assumptions on the probability distributions and the initial conditions. Okay, so knowing that a solution exists is not really relevant yet, because we still need to relate the existence of these solutions to the finite gradients, stochastic gradient descent iterates, either for this or for noisy SGD. Okay, in order to do this, they have a kind of sort of very general result that applies both to SGD and to noisy SGD and proves these convergence bounds. The assumptions that they need are mostly kind of standard assumptions on the activation function regularity, sort of sub-Gaussianity of the activation function gradients, sufficient smoothness in U and V, and also a particular shape of the infinite step schedule, although you're free to just assume that that this function is just constant, I think, for the purpose of the proofs. Okay, so what's the main result here? They end up showing something like this. So if you start with an initial distribution on the weights, then running SGD with this particular step size and initial weights sampled from row 0, then you have almost sure convergence to the distributional dynamics with this particular choice of step size. So this is the floor of t divided by epsilon, where epsilon is epsilon n, a sequence that effectively tends to 0 under these constraints. Okay, so this almost sure convergence is effectively the result that you want, and the important thing to have in mind is this extra scaling that you need in the step size according to the error that you want to incur in the approximation. Okay, so this is good, and furthermore, you want to obtain some bounds, right? So you want to obtain some bounds on quantitative measures of such as the outputs of the neural network or the risk. So the idea is here that the supremum over all steps up to a certain capital T of the differences between the empirical things and the sort of the equivalent distributional solution integral versions, right? Both in any bounded Lipschitz function or in the risk itself, they're bounded above by this quantity here with high probability. And importantly, these bounds hold exactly the same way, both for SGD and for noisy SGD. For noisy SGD, you need some bounds on the temperature parameter as well as the regularization coefficient. In particular, the temperature has to be positive and bounded below by some constant. So it doesn't work for values of the temperature tending to 0, but that's okay. And the interesting dependence, again, is here in the right-hand side. So you see that the dependence on the width of the neural network and also on the error, so the epsilon itself, and also on D, is fairly benign. So the data distribution and the dimension of the dimension of the weights themselves and the dimension of the number of weights themselves don't factor heavily into this bound. On the other hand, the t here factors exponentially. So this is to say that you expect to incur exponential error as you keep taking SGD steps, and in order to mitigate this, you have to effectively scale n. So you need to let n tend to infinity much faster than t in order to compensate for this. Okay. This is maybe interesting. I don't know of, so there are various other papers that give similar results in slightly different settings, but I don't know of any type of mean field result that doesn't have an exponential dependence on t here. And there may even be some a priori lower bounds that say that this cannot happen for for arbitrary data distributions, let's say. Okay, so before we look a little bit of, so the idea behind this proof is going to be fairly simple. It's going to kind of be step-by-step relating the finite SGD iterates to a kind of a continuous sample from the distributional dynamics. So to trajectories sampled from the distributional dynamics, and kind of bootstrapping them step by step and accumulating these bounds. So we're not going to talk in detail about that, but before we have a quick look, let's see, maybe some results, some visual results of what this theorem implies.
What's capital K?
It's just a constant. They're not actually even the same constant. It's just you're free to kind of assume large enough constants here that don't depend on any of the other named constants. So don't depend on t, on n, on d. These are just constants that depend on Lipschitzianity of u and v and g in this case, on boundedness of g of the gradients of u and psi. Right, so they depend on these kind of systemic constants that don't change throughout the problem.
Epsilon is the learning rate, right?
No. Epsilon times psi of k epsilon is the learning rate. Yes.
Okay. No, I was wondering because it seems epsilon must go to 0 when number of neurons go to infinity. Is that right?
Epsilon must go to 0 when the number of neurons goes to infinity. Yes, for these conditions to hold. Yeah. Yeah, for this condition to hold. Yeah.
And so this is kind of, so I have an intuition for this. I just wonder if that is correct, because when you have a number of neurons that grows, then also the gradients tend to grow, and so you must take a small learning rate to counteract this effect. Is that
yes?
Reasonable? Okay.
Yes. I mean, so okay, so there's two things here. So the direct answer to that question is, I think it's a good question, by the way. I think the direct answer to that question is no, because you're already scaling by 1 over n, remember? So all of these expressions.
That's why I thought maybe there's something more.
Yeah, so I think that there is something more. I think that these particular expressions for epsilon just kind of analytically come out of the proof. I don't think. What do I think? So if you think about it, a lot of things will satisfy this. A lot of decreasing schedules will satisfy this. So in particular, it's not. How should I say it? It's not necessary for epsilon to go to 0 if psi if psi goes to 0 as k tends to infinity. Am I right?
Well, what's psi?
Psi is this extra kind of scheduling function which comes in to the distributional equations. Yeah, here. But let's quickly go back to the so here, if epsilon doesn't tend to 0, so it's bounded below, then this will also not tend to 0. So epsilon has to tend to 0 from this condition anyway. Okay.
Yeah, that's fine. Please continue.
Okay. Yeah, so yeah, what I wanted to look at was kind of what this whole process, you know, what the picture behind this process is, to kind of have a small visual representation of what's going on. So they actually do these two experiments in the paper. And not only do they do these experiments, but they also kind of analytically compute all of the quantities involved, yeah, give numerical evaluations for their method. So the idea is that they would like to consider the problem of classifying or separating two isotropic Gaussians with dimension small d, and they're parameterizing their Gaussians by this sort of delta parameter. This is to say that the Gaussians labeled 1 have larger variance than the Gaussians labeled -1. Okay, so you can think about this as a binary classification problem with the with the point of finding an estimator that correctly labels A or B. Now, of course, if you had a way of computing, you know, of computing delta, or of computing just the squared norm of the sample x, then the squared norm of the sample x passed through something like a sigmoid would be a very good, you know, would be a very good estimator it would be a very good classifier. Right. But the idea being that it's not exactly easy for a shallow neural network to directly learn this classifier, and even if it was, how can you make sure that you get there through SGD? So in the following figures, they give you the representation of the weight distribution at various iterations in SGD. And also the theoretically computed solution to the PDE. So rho t at the appropriate time with the correct time scaling, I guess. And obviously, you see there's a good match between the empirical and the theoretical distribution. And even though these things look very different at individual time steps, the evolution stays consistent. So that's one interesting observation. The other one.
So isn't the approximation supposed to be? I mean, the iteration 10 to the 7 should be worse. The match between SGD and PD should be worse because of what you said, that there's an exponential error in the number of iterations.
Yeah, it's true, but I think that they are free here to for example, to pick an epsilon that that achieves a certain error bound on all of these, right? So you can, for any finite amount of steps, you know, pick an epsilon that gives you low error.
But this epsilon should be exponential. This epsilon should be exponential in the number of iterations, right? So it should be exponential in 10 to the 7, which is like, I mean, it should be 0, no?
Yes, but also no, as in you don't really know the constants for the finite. So exponential is just an asymptotic statement, right? It's not really telling you what the constants should be for any finite time. The values themselves that they use to generate this picture, I think they're in the paper. If you're interested, you can have a look in their appendices. And yeah, I don't think anything particularly, let's say, particularly suspicious is happening here. So all of the values that they use to generate these pictures are kind of let's say mundane with respect to what you might expect. So there aren't any absurd numbers, billions of neurons or anything like that. Okay. Yeah, I don't know. I should say I don't know exactly what the values are off the top of my head, but we can have a look at the paper and try to figure it out.
That's fine.
Yeah. Let's see. So yeah, so epsilon is 10 to the minus 6 and n is 800. And this is for all of these, and d is equal to 40. So small d is equal to 40. So the dimension of the data. So again, yeah, the values are chosen obviously to make this picture work, but they're not absurd. All right. So they also give you the dependence of the risk on the parameter capital delta. Obviously, as capital delta becomes very, very small, the two distributions become indistinguishable. So this is not a surprise. But again, you can see that the theoretical prediction for the risk and the empirical computation after a single run of SGD across the entire data set, they stay quite good. So this is only a single run of SGD across the data set. And you can also see the same risk in terms of, in this case, the number of iterations across different separation parameters delta. And again, the predicted distributional dynamics and the SGD, they stay fairly close for all times, with a kind of a uniform choice of the step size epsilon and the number of neurons. Okay. So yeah, these are kind of the pictures of what's happening. So what is happening behind the scenes is, in order to show that the kind of the finite time SGD iterates stay reasonably close to the distributional dynamics, you need to figure out you need to figure out a random variable, right? So you need to figure out an object that looks like a sample from the trajectory generated by the distributional dynamics. And it turns out that the correct thing to define is this capital theta, which satisfies this integral equation, which again is expressed in terms of the potential phi, and the rho s is precisely the rho s in the distributional dynamics, and it is the law of theta is. So this particular integral form for the trajectory is something that you see in a lot of mean field papers. Okay, so the important thing about these things is that the way they were defined, and because they start independent, they stay independent. So again, the empirical sum over the individual trajectories for each I, this will recover rho t for you. So this looks like the right object, and it turns out to be the right object to consider. So this is kind of the central lemma behind the proof. So again, once you know that all of these solutions to the distributional dynamics exist, you can define this theta in that particular way, and you can bound the supremum over all time steps of the difference between the finite thing and the kind of the nonlinear dynamical process by basically something that looks like the error term that we're interested in with high probability. And again, this is done by bootstrapping. So this is done by kind of applying martingale inequalities such as Zuma-Hofting and integral differential equation inequalities such as Grunwald's to kind of split the difference between theta, small theta and capital theta into a sum of terms, and individually bound them by sums that by terms that depend on this error. Okay, so this is not particularly instructive exactly how these inequalities are applied, and they're fairly it's a fairly common method of proof, I should say. So that's all we'll say about this. And the next step that they do in this paper is to look at the statics. Okay, so up to now we haven't really done anything. Everything that's happened so far is saying that, okay, we have some finite time stochastic gradient descent iterate, and under suitable assumptions, this stays relatively close to the evolution of the distributional dynamics. But this still doesn't tell us anything about the value of the risk. Okay, it doesn't tell us anything about what happens at convergence for SGD. And in particular, it would be important if we had the similar results for the distributional dynamics, right? Because if we knew that the distributional dynamics converges to a local minimum or to a global minimum, so to a fixed point where the value of the risk is good, then using the fact that the finite SGD iterates approach, or the risk of the finite SGD iterates approaches the risk of the distributional dynamics, then we would have some result there, right? So this is the idea, to look at the fixed points of equations 61 and 63. Okay, so equation 63 is very well studied, and we have a very clean and nice result on the fixed points that we'll show in a second. However, the fixed points of equation 61, so that's the one corresponding to honest to God normal SGD, those aren't as easy to classify. And in particular, we don't have any sort of uniqueness result on fixed points. And the best that we can do is kind of say that, kind of give a characterization of fixed points in terms of the expected support that we see for the distribution row. So in particular, they're exactly the ones for which the support of rho, and I'm missing an equals 0 here. So they're the ones where the gradient with respect to theta of the potential is equal to 0. So the idea being that if you vary theta in any which way and in any which direction, then in this set of fixed points, the potential doesn't change that much, which is kind of natural given how rho was defined. Of course, going the other way, it's a little bit more difficult, but nevertheless, this also gives you a fairly interesting result on the types of distributions that you can expect, because if you put in sort of appropriate analyticity assumptions on U and V, then you can get that this is an analytic function and you'll very easily be able to extract the fact that because the zeros of an analytic function have to have Lebesgue measure 0, then so will the support of rho star. So in particular, rho star looks like something that is supported in a very small set, and typically, and also true for one-dimensional examples, they will be a sum of delta functions. You can use this. They do this in the paper. They use this condition to give an exact expression for when the fixed points of equation 61 are precisely a single delta function. So we know that delta functions can be fixed points, but single delta functions may not be fixed points, and they treat this example they treat this example separately. Well, okay, so this is kind of interesting, which is to say that you do expect these limiting distributions of weights to be supported in a very small set. That being said, for the Fokker-Planck equation, the story is somewhat different. So again, as we saw in part 1, this can be recast as a Wasserstein gradient flow for the free energy, given by this formula here. Remember, last time it was basically a sum of the risk plus an entropy term with a particular temperature. This also has a regularization term, which you can subsume into R rho. So because of this, you can also show and it's a fairly classical result, that these equations admit only one fixed point of finite energy. And if we start off from a distribution that has a density, then our fixed point also has a density, and this density satisfies a kind of a Boltzmann potential form. So it's and the actual expression is given here in terms of beta, the temperature, and the potential psi. Okay, so we basically know what the statics of equation 63 are. So we can use them to have to study what happens for the finite time SGD iterates. So obviously, because of the existence and uniqueness of these fixed points, the distributional dynamics will evolve to rho star, and you can write out. We can effectively combine theorem 3, which we had a look at, which was the bounds on convergence of the finite iterates, to get inequalities between the expected risk at the unique minimizer of the free energy, and the infimum overall parameters of the finite risk, so of the risk of the neural network. Again, the temperature parameter and the distribution of the weights plays a role here, but the idea being that as you pick the temperature of the SGD updates to be higher and higher, this approximation becomes better and better. Okay, and the reverse result is you also want to bound the empirical or the risk of the finite neural network by the infimum overall possible distributions of the distributional risk, and here this is again also possible for beta large enough and for k large enough, so for a long enough number of gradient descent steps, to bound the risk that you see in practice by the theoretical infimum of the distributional risk, plus some small quantity which will factor into the probability of this happening. So it's 1 minus c to the minus beta squared, something like that. Okay, So this is to say that, by and large, with obviously all of these error terms taken into account, the risk of the finite number of neural network approaches the sort of the theoretical lower bound for the risk of the distributional dynamics. So this gives you, for noisy SGD, it effectively gives you a convergence result to a global optimum. So this was kind of the first result of this type that I think appeared in the literature. And again, for typical SGD, because of the lack of uniqueness in the fixed points of the distributional dynamics, you can't really recover this. And I think that in this sense, this type of result is more or less unique. And whenever the statics of the distributional dynamics is easy to analyze, then you can hope to recover something like this. But in practice, this is quite difficult. And we'll see if we have time to go through this next time. We'll see that effectively for deep neural networks, this is not really the case again, and it doesn't seem like it can be mitigated by the noisy SGD dynamics. Okay, so I think that's all I have for today. Yeah, thank you for being with me till the end, and happy to answer any more questions.
I have a quick question. You showed some training curves.
Yeah. This or this?
Yeah, this.
Yeah.
No, I guess I wonder if running. Wait, but this is PD and SGD. So it's not okay. So this is PD is running the Fokker-Planck equation, right?
The PDE is running equation 61, I think.
Okay. No, because I wonder if it makes any sense to run this equation to predict the training dynamics, if it's more convenient than running SGD, but I guess it's not, right? So because one could argue, okay, what do I do with this? Maybe one thing I can do with this framework is I can run the equation 61. I can solve equation 61 numerically instead of running SGD, and because then I can figure out how my training of my risk will go without actually doing the running SGD. So the question is it convenient at all, or is it actually more, is it takes longer to run the equation 61, or it takes longer to run SGD?
I mean, I don't think you can run equation 61 so it really depends what you mean. So you might have situations where you can compute the solution to equation 61 exactly, like they do for separating the Gaussians. And other than that, you might need to rely on numerical methods.
Yeah, I'm saying numerical methods. I'm talking about numerical methods. So if you run this, these are numerical experiments, right?
I think not. No, I think not. I think these are analytic plots for the PDE.
Well, but regardless, you can still solve question 61 numerically and ask yourself, is this more convenient than running SGD?
Yeah, you can. I would think that no. If you want to get numerical solutions to the PD, especially in high dimensions, right? So you have high data dimensions. If you want to get, and high weight dimensions, right? If you want to get numerical solutions in such high dimensions, this is a kind of a hopeless problem. So people don't really solve PDs numerically well in such settings, whereas SGD is always very cheap, right? So
yeah, that's what I thought.
Yeah.